Hello, everyone. Can you guys hear me? Great, thank you. I'm Dr. Chen. Thanks for signing up and attending, the review session. I may have to, mute all of you guys since, there are so many students online. Let me see. So if you have any question or you need to, talk to me due to any reasons, so you can try to type, okay? Let me see, how can I, mute all of you guys? Here is mute myself. Does any of you know how to mute all of you? No, kind of one by one? Mute the application. I didn't see anything. I think here is mute myself. Okay, anyway, I think right now it still works. So apologize, I got late a little bit. I got some traffic in the night. Oh, there's someone who cannot hear anything? It seems like most of you guys can hear me, right? Great. If there is some people who can hear me, which means theoretically all of you should hear me. So if you cannot, please check your, audio and other related devices. I think in the mainly in the audio, device. Okay, can someone, help the others if you can talk? I think it's in the bottom left. There is kind of, the video and the audio. Okay, give you a 1 or 2 minutes for you to figure out, and then I will try to show my iPad. Okay, I think you can all see my iPad, right? Okay, for those who are, not able to hear me, did you solve the problem? Okay, okay. Try your best, solve the problem. Yeah, either you rejoin or, you try to open your audio device. This is the first review session for the USNCO 2020. Probably it will be the last review session for the local exam, because as you know, tomorrow will be the first test day for local exam. So I will not going to have any more, review session for the local exam in March. But probably based on my time and your interest, we might, have a few review sessions, in April, or, probably April for the national exam. Okay, if you guys are all ready, let's just start. So probably you already, get my email. Since we only planned for 1 hour and there are so many topics and so many contents we can discuss or we need to discuss. So I can only choose, those topics which has a certain level of difficulty and also a relative high repeatability, which means it's kind of, showed up almost every year in the past 3 to 4 years. And so I kind of, briefly summarize a guideline like this. So I will only talk about the underlying topic tonight. If we can finish earlier and we still have some time, we can talk about the others. But probably if we can finish those, it will be already pretty good. So let's just start. You guys all know there are 10 categories in the local exam and the national Part 1. So the first category I want to discuss is the second one, descriptive chemistry and the laboratory and solubility rule. I think you guys all know solubility rule. Here, I only want to pick up a few, like chlorides and fluorides. So for chloride and fluorides, chloride actually represent, the halides, let's say X minus. But fluorides have some special property with the other halides. So this is why I kind of, make a comparison here. For example, all of the silver halides are precipitates with different colors, but these are precipitate. Now use this kind of symbol to represent they are precipitates. But you may know silver fluoride is not, right? This is a very good comparison. This is soluble, so which means you can have an aqueous solution. And another example is the Ba barium fluoride is a precipitate. Barium fluoride is a precipitate. But the other barium halides are not. So this is also a good comparison, right? Obviously, we can use this, this kind of pattern to further extend a little bit. For example, copper 1 plus are in the same group as silver 1 plus. So you can expect copper 1 plus halides are also precipitates. And also, let me see. Another one is I think that should be enough. Copper 1 plus. And for this one, barium fluoride, you can extend a little bit to the other, group 2A elements, the alkaline earth metals. For example, like strontium fluoride, like calcium fluoride. So you can expect those are also precipitate. Similarly, you can also expect those kind of group 2A elements halides, like strontium chlorides, calcium chloride. They are not precipitates. Did I make it clear? Let me know if you have any question. I will also pay attention, to the group chat. So those are the a very interesting comparison. It seems like there is no very good reason to explain. For the color of the precipitates, there is really no good method. Theoretically, you should accumulate through your chemistry class, by doing all kinds of experiments. But since some of you might not have the opportunity, or even you take the chemistry class, there might not so many labs related to the colors, the solubilities. So you can only accumulate by experience, which means you may need to pay some attention to the colors. But the good thing for local exam is it will not assess you the colors in a very high degree. So I think it should be fine. You just need to know which are precipitate, which are not. But there's no guarantee, okay? The more you know, the more confident you can be. The second one is kind of a new topic, showed up in Local 2019, is about the sulfide. We know sulfides, most of them are precipitates, except a few, like sodium plus, potassium plus, ammonium plus, right? Ammonia actually is quite similar to the alkaline metals, like sodium plus and potassium plus. So which means most of the others are precipitates, but they have different KSP. Oh, yeah. This is a good reminder. So if you know how to mute yourself, please, try to mute yourself. I can do it manually, but I don't know what is kind of the systematic way to mute everyone. At least at this moment, I couldn't find it. There's no other, exceptions. Sodium, potassium, ammonia. Those are the most important three, representatives of exceptions. So most of the others are just precipitates, but they have different KSP, which means their KSP varies. But how do I know what kind of sulfide is more insoluble? Which kind of precipitates has a lower KSP, right? So here we may need to briefly talk about the hard, soft, acid, and base theory. So basically, we can divide the acids and the base And here, the acid and the base are classified by Lewis acid and base theory. So if the acid is harder, it will have a higher affinity to bind with the harder base. For example, like H+, this is an Lewis acid, right? This is Lewis acid. So it can strongly bind with a strong or hard base. For example, like, F-, like hydroxide. So how to define, hard and soft? So basically, hard means higher charge, small size, and high electron activity. So here, as you can see, H+, the size is very, very small, right? So definitely it's very hard. For the bases, it's quite similar. So F- hydroxide, they have high electron activity. So which means their electron cloud are kind of, attracted to the nucleus and make the size relatively small, make the electron cloud more kind of, holded by the nucleus. So this is called hard-hard. So the hard-hard combination will have, strong affinity. And also some, for example, let's say mercury 2+. This is a transition metal with, let's say, the d orbitals. The d orbitals are relatively loosened. So this is why this is called a soft acid. And then S2- compared to O2-, F- is also relatively soft because it has more layers of electrons. It also has a relatively low electron activity. So this is kind of a soft combination. So the key point of HSAB, hard, soft acid and base theory, is hard, strong affinity, soft, hard, strong affinity. So this is why the mercury sulfide has a super low, KSP, and then which means they bind strongly with each other. For polyatomic ions, you mainly focus on, which atom is the real one to bind with others. For example, let's say nitrate, sulfate, they pretty much use oxygen, so they are pretty hard. But the hard and soft are relative. So by using this mechanism, so let me give you a small question for you to think about. So let's say you have zinc sulfide and cadmium sulfide. So can you predict which one will have a relative lower KSP? So if you know the answer or you have a kind of a guess, you can tell me. So we already know sulfide is soft. So we need to pick up which cation is softer. The softer the cation is, and then the stronger combination of the cation and anion will be, and then the lower the KSP will be, right? So if you check the periodic table, you can quickly find out zinc and cadmium are in the same column, they're in the same group, right? So can you tell me which one is softer? The zinc 2+ or the CD 2+? Obviously, the cadmium is softer because it had one more electron layer, right? So if the cadmium is softer, it should have a stronger combination with the sulfide because they are soft combination. So from this perspective, the lower KSP one should be the cadmium sulfide. And then you can further check the KSP to double check. So I will not show you here. I think you guys can do the homework by yourself. So this can be an example to show you, right? So now I give you one more to think about. So now I say another one is calcium sulfide versus zinc sulfide. So can you tell me which one has a lower KSP? Give you one more chance. A lower KSP means the KSP is smaller, which means a lower solubility. Makes sense, right? So what I'm saying is the cadmium sulfide will have a lower solubility than the zinc sulfide. Okay, my new question, calcium sulfide, zinc sulfide, don't do any searching about the KSP, just use the HSAB you just learned. to have a conclusion. Which one should have a lower solubility? So the key question is calcium 2 plus softer or zinc 2 plus softer, right? Soft has a bad solubility because they have a stronger combination. So they want to bind together, which means it does not want to dissociate. Does this make sense to you guys? Yes, exactly. Sulfide is a soft base, is a very soft base. So due to the limitation, because I'm using the the regular Zoom, so we may need to restart every 40 minutes, okay? So I will plan, we probably need to take 2 40 minutes, in total around 80 minutes to finish the session today, okay? So and then if you automatically quit the meeting, and then please rejoin by using the same link later, okay? We have a little bit less than 10 minutes. Okay, so the conclusion is the zinc sulfide will have a lower solubility because zinc 2 plus is softer than calcium 2 plus because they are in the same periods, and zinc 2 plus has 10 3D electrons, right? Which will make the electron cloud a little bit loosen and make the zinc 2 plus softer. So you can imagine, the electron cloud are like what that called? Like the cotton, right? So if there are more electrons, so the electron cloud are loosened, right? I think this is a good summary. So in order to determine the relative hardness and softness, the 3 factors we should look at. First is the size. Second is the electron activity. The third one is the charge. Typically, higher charge means smaller size, right? You don't need to record the session. I will record it, and later, I will share, the video in my website. But probably will lose, the group chat contents. You only have the audio and the video. Okay. Okay. Let's move forward. I think there are some other important solubility rules. The most important you need to know is sulfates. So there are a few important precipitates made by sulfates. The first one is barium sulfate. I think this is the most important one, the barium sulfate, okay? Okay, I cannot, use too much time here, so you guys can use this kind of concepts to do a little bit more homework after this session, okay? I hope I make it clear. If you still have a question, you can let me know. Oh, the Google Classroom. To be honest, I didn't, take care of the Google Classroom pretty well. I even didn't, log into for a while. Okay, let me double check later after this class. Because, when I started the Google Classroom last year, it seems like there are not so many students who are active, who are interested in the Google Classroom. And even there are some guys who kind of post some unrelated stuff every day in the Google Classroom. So I kind of, I forgot that. Apologize. I will have a look. Okay. Okay. The next one is called volumetric glassware. I want to kind of, summarize a small table. You guys can summarize your notes based on you need. Okay. So the first type is called TC, another type is called TD. What is the full name? TC means to contain. TD means to deliver. What does it mean? To contain means the amount in the container is accurate. But when you dump it out, the volume might be smaller because there will be some liquid, still on the wall of the container. And to deliver means, when you dump it out, the volume is accurate, but actually it might include more stuff inside, right? So for example, let me give you a few examples. First, let's say the most precise to contain for TC will be the volumetric flask. You guys know what is the volumetric flask, right? A volumetric flask has only one mark. So this is why it's called to contain, right? And then to deliver, the most precise one are like pipette, burette, and like graduated pipettes, or volumetric pipettes. So how do we know they are precise? Because they can read to 0.00 milliliter. So basically, you can have two significant figures after the decimal points, So those are the three types of precise glassware. One is TC, another one is TD, right? And then there are a few less precise. Obviously, for the TD is the graduated cylinder. Typically, they can read to 0.1. Let's say not 0.0, 0.01. Here, most likely it can read to 0.1. And for TC, I don't think we have anything for TC here. And there is also some glassware which are not precise at all. So which means they are barely used for volumetric analysis. For example, for the to deliver is like beakers, right? Like flasks, the Erlenmeyer flasks. Okay, I saw you guys are still discussing the HSAB. Definitely, it's not this kind of straightforward. Especially, it's the first time for you to hear about the HSAB. So you guys can do a little bit more research, after the class. And then, if you want to, get a little bit more about this, you can read my annotations, for the local exams in my websites. Okay, TC I think is down here. TC TD is not so important for you to know, but I just want to kind of differentiate them for you to have a good understanding. So choosing the best glassware to satisfy your requirement is also important. You need to find the right glassware for the right thing. Yeah, we have a little bit more than 2 minutes left for this session, and then I will restart and you guys can join me later. Okay, again. I will skip the error analysis here, but you might use the 3 items I listed here to think about. Oh, I want to briefly talk about the rinsing. For example, you typically put your analytes in the flask, and you put your titrant, which is kind of a standard solution, in your burette, right? So I want you guys to analyze, if I use water to rinse the flask and use water to rinse the burette, which one will result in some error, which one will not? So the question is, if I use water to rinse the flask and the burette, which one will produce some errors and which one will not? Yeah, obviously the burette, the rinsing burette will produce the error because you will dilute the standard solution in the burette. So how should we solve this problem? After you rinse the burette with deionized water, you need to use your standard solution to rinse the burette 2 to 3 times again, right? It's rinsing, it's not washing, okay? So basically you dump a little bit and then you put the burette kind of in a flat position, and then you dump the solution and do it several times, right? And how about the flask? The flask will not produce any error, right? because we only care about what is the moles of the analyte in the flask. And adding water to the flask will not change the moles. And actually, during the titration process, we are going to add some water in case there is some kind of, standard solution sticked on the wall. So we need to use the water to rinse the flask, right? So this one will not result any error, okay?